Right. So today we'll be discussing, among other things, no? Well, we'll be rediscussing ideal of amps, no? What kind of assumptions do we have that make op amps ideal? And then we'll compare that to, well, real op amps, no? Or at least a little more realistic na model ng op amp. And then we'll discuss some other non-idealities, no? Specifically, what makes these op amps real is, well, some of them are linear, which we can put into the model, and some of them are non-linear that we can also still put into the model but are a bit harder to address. And you probably, if you've done op amps in a lab class, have you guys, touched op amps in lab classes before? Yes. Okay. So you'll be a little familiar with the pinouts and why we have okay. So we'll be talking about why we have these other weird pins in our op amps that don't seem very necessary, no? So let's go back to the op amp. So ang symbol natin for op amps are always triangles. Then again, our symbol for most things is actually triangle, no? Not just op amps. But it has these ports, no? So we have V minus port, a V plus port, no? So you call this the non-inverting input. Sorry, nasa baba yun na non-inverting because it's plus, no? Yung minus na input is your inverting input, no? And then we have two more pins here. We have the uh, positive voltage maximum and negative voltage maximum. So that's your positive supply. This is your negative supply. And then you have your output, V out, no? So essentially, what an op-amp seeks to do, right, is to amplify the difference between our non-inverting input and our inverting input, multiply that by the gain of the op-amp A, and release that as the output voltage. Ideally, that's what we wanted to do, no? So, all of this naman has probably been discussed before, no? Yung different parts ng op-amp, we've even touched them in the lab, so you probably know all of these ports, no? Now, in reality, if we try to dissect an op-amp, you'll see it's something like this. Meron tayong V minus, V plus, and then maximum, minimum, output. Now, sa loob, we actually have a resistance between the two inputs, no? So, um, in an ideal op-amp, right, our assumption is that the current going into these ports is zero, which is a reasonable assumption because Rin is typically huge, no? But in reality, Rin still exists, no? There is still a current that is induced by the input into the input ports of an op-amp, no? And that's the input current Rin. Now we also have here, no, finally, yung output, no? So we call the A the open loop gain or just A, to be honest, because we're not really talking about um okay, never mind. We are talking about closed loop gain most of the time as well. So yes, that's the gain of the op amp essentially. And then dun sa slides, ang tawag natin dun sa input voltage is the E na D, which is the differential input voltage. Now we refer this to ground. And before we get to the output, we actually have an output resistance, no? Now, Kung ideal yung load natin, meaning na hindi natin kita yung resistance niya or infinite yung resistance load, then of course, we just ignore R out. No? Kaso, the reason for R out being there is because there can be load, no? Na ang mangyayari, no? Okay, ano mangyayari kapag naglagay ako ng load dito, no? Let's think about it. Na kapag naglagay ako ng load doon, we have the gain, the open loop gain times the input voltage. Tapos meron tayong R out, tapos meron tayong load, no? So what happens is we have the voltage divider, right? So the output resistance of the op-amp signifies that depende dun sa output load resistance, magde-degrade yung voltage na nilalabas natin, no? And this is kind of bad. Why? Kasi um have you guys messed with the 50 ohm speaker? Nabigyan na ba kayo ng 50 ohm speaker sa lab? So there is a thing such as the 50 ohm speaker. And if R out is comparable to 50 ohms, then babagsak yung gain mo, no? Babagsak yung output voltage mo kasi magvo-voltage divide siya, right? So that is the non-ideality that is presented by R out, no? So let's remove RL for now. And this is your circuit model of an ideal op-amp, no? Or semi-ideal, no? To be honest, we have differing degrees of non-ideality na ngayon. But this is your circuit model of an op-amp with the without the non-linear idealities. So, di ba nasabi natin, meron tayong linear at saka non-linear idealities. For the linear model, for the linear non-idealities, we can take care of those with the circuit model. All right? So, let's copy paste this and try to analyze it further, no? Or we'll copy paste it, but we're not going to analyze it further. Sorry about that. Ang gagawin natin, we're going to create the ideal op-amp from this non-ideal model, no? So, the ideal op-amp involves a few things, no? So, tatanggalin natin tong resistor na to, and we'll say that approaches infinity, no? Essentially, there is no connection between the inverting input and the non-inverting input, no? I like to call it, to be honest, as a short na open, essentially, no? Kasi, naka-short itong dalawang to because typically, no, in the feedback setup, equal yung dalawang input ng op-amp, right? Remember the feedback setup? Kapag in-round natin to, this is also 0 volts, right? So, naka-short siya. Kaso, walang current. So, ang tawag ko sa kanya is short na open. And the reason that we can say, no, na short na open siya is because walang current na pumapasok dun sa inputs, no? And that's because in ideal op-amps, we assume that the input resistance is infinite, no? So that's one part of the ideal op-amp, no? So part one of the ideal op-amp is that the input resistance is infinite. Now, part two of what makes the sige, baguhin natin yung kulay para maganda. Part two is that the output resistance should ideally be, no? So to be able to support any load, like for example, the 50 ohm speaker, right? Dapat yung voltage divider natin as like dapat walang voltage divider na mangyari. So ano ba yung voltage divider na yun? That's R out plus RL, right? times AOLED. So, ano mangyayari dito para maging ganito na lang din siya? Ah, para magiging ganito na lang, para maging ganito na lang din siya, AOLED, no? So, tama na yung voltage na lumalabas. You want R out to be very small. That's correct, no? So, in an ideal op-amp, R out approaches 0, no? So, we actually turn that into a short circuit, no? Lastly, number 3, for an ideal op-amp, the open loop gain is infinite, no? This completes the first part of short na open, no? So, um, ito yung open part ng short na open between these two, right? And this is the short part of the short na open, right? Because if the open loop gain is infinite, then this is infinite, right? Or we can do a little bit of circuit manipulation, or we can do a little bit of manipulation, no? To show na non-inverting minus inverting times ito, no? Remember, ED is just non-inverting, non-inverting minus inverting, no? So we can show that this thing, which is equal to V out, for finite V out, which is always true, no? Kasi never naman tayo nagkakaroon ng infinite voltage. So we can see na the non-inverting input must be equal to the inverting input, right? Kasi equal to 0 to. Because AOL, the open loop gain, approaches infinity, no? So this is the short part of the short na open, and Rn being infinite gives us the open part of short na open. All right? By the way, does that make sense? Anyone have any questions about how we turned the model into the ideal op-amp again? Why not just remove R out? But essentially what we did was remove R out. Yeah. So since R out equals 0, then we don't have to draw it in the circuit anymore, right? Which is what we have here, no? So wala tayong dinrawing ng R. What we have in this plates is an open circuit, and what we have in the place of R out is a short circuit. So yun nga, niremove natin si R out essentially when we let it go to 0. Bakit naging 0 ang V out over AOL? So V out for most circuits is finite, right? Or for all circuits, no? Never naman tayo nagkakaroon ng infinite na voltage, no? So which means that if it's divided by an infinite value, goes to 0, no? So the limit of this, as the bottom one goes to infinity, is always 0. But essentially, all that we're trying to show here is that um, the open loop gain being infinite, no, implies that the non-inverting input has to be equal to the inverting input for finite na V out. ED equal, this is, so this is always true, no? So ang ina-amplify ng op-amp natin is always the difference between the inverting input and the non-inverting input. So essentially yung ED na yon is just KVL on this initial model. Alright? Sige. So, let's move on. Ayoko na itong blue na to actually. We kind of used that last time. So, the steps, no, is check for negative feedback. And then, no, check for negative feedback. If so, use yung regular analysis for feedback op-amps. So you've seen that a lot naman na, right? The way you analyze that is by assuming the short open thing, right? To get the gain, which is R2 over R1 of V in, right? So, and you've definitely seen that in a class before. So we're not going to be covering that one. Next is, no, once we're sure na hindi negative feedback yung nangyari, then we assume linear operation. Now, ano ba tong linear operation? Itong linear operation is when we can compute the gain as open loop gain times the input, no? That's times the input voltage, no, which is ED or V in, no? And assume that that's V out, no? We also apply the assumptions for ideal op amps, no, which is V plus minus V in equals 0, and well, I plus and I minus are both also 0, no? So actually, sige, let's do it like this, no? This is for non-ideal, this is for ideal. All right? Next is kung hindi kumana 'yon, no? We're gonna need to check, no? Um well actually, okay. So after mo i-apply 'yon, mag-KCL at KPL ka muna. Kaso ang fourth step is check, no? Kasi meron tayong maximum voltage at saka minimum voltage, right? Which is given to us by the top and bottom ports of the op amp. Itong V plus at saka V minus, right? So, we need that, we need to make sure that V out remains within that range, no? So, if not, then you rail it, no? So, kapag masyado siya mataas, then you put it here and then do the analysis again. Kapag masyado siya mababa, you put it there, no? V out equals this, and then you solve the circuit again, no? So that's what happens for railing, no? Kapag saturated, no? So you call this saturated na yung op amp. All right? So those are 4 steps for the analysis, no? Which is included in the slides naman, no? So you can check again the slides. But to be honest, I don't really follow this rigidly. I think I follow it naman by heart kapag sinusolve ko. But the thing is, it's just a successive um it's just a successive step-by-step process, no? Kasi of course, hindi mo naman malalaman kung saturated yung op amp unless you know na magiging greater than or less than yung output mo dun sa saturation conditions, right? So that's why it's step 4. Also, kapag negative feedback, of course, hindi mag-a-apply itong gain natin, right? Kasi mapapalitan yung gain natin no feedback na gain, right? So that's what the steps are for analyzing op-amp circuits. Next, let's talk about real op-amps. No? So, di ba ito, describe natin dito kung ano yung ideal na op-amp. Well, again, no, the real op-amp would be what we had before. No? So we have this. No, this is your ideal op-amp. So you have the linear non-idealities. Ito, no? So we have the finite open loop gain. We have the finite open loop gain, no? So this is less than infinity. We also have the finite, no, na open loop, na input resistance, no? So yung Rin na nakita natin, this thing, no, is now not an open circuit, no? So it's not infinity. R out is also greater than 0, no? So this is not a short circuit. And that's your linear non-idealities, including a fourth one, which is that finite yung bandwidth natin, no? So let's talk a little bit about a finite bandwidth, no? So the finite bandwidth actually is something like this, no? It's shown in the slides. Kaso, what you can see here is that typically, actually no, I don't like this graph too much. Sige. So for real amplifiers, usually ganito yung itsura nung gain nila, no? So at low frequencies, so at like 1 hertz, 10, no? So 100, 100 plus 1K, no? Hertz as in yung frequency, no, nung pinapasok nating signal. So magsa-start ka at the full gain, of course, right? Kaso, after some frequency that you call the bandwidth, no? Magsisimula nang bumaba yung gain ng amplifier natin. Ne? And then at some point it becomes 1, no? Which is the you call the FT or the transition frequency. So it transitions from being an amplifier to not an amplifier in the transition frequency. No? All it's saying is that this happens for for real op-amps. No? For ideal op-amps, this does not happen. No? We assume na constant yung gain no matter what. Right? So these are your linear non-idealities of the op-amp. Essentially, when you put in linear non-idealities, you just get this model back, no? Yung circuit model natin. Right? But there are also non-linear non-idealities. So ang non-linear non-idealities natin is like so itong mga to, no? Input offset voltage. So essentially, ang nangyayari dito, right? You have the op-amp, you have the V minus, you have the V plus, you have the output, no? Ang nangyayari is, meron ka ng, like, yung op-amp, meron siyang nakikitang difference between our inputs that shouldn't be there, no? So essentially, if you short these two, dapat ang input mo is 0, right? Kasi pa equal si inverting at saka si non-inverting input. Kasi si op-amp, in this non-ideality, may nakikita siyang voltage difference, no? And this is your offset voltage. So that's your input offset voltage. And you've seen this before. Well, rather, you've seen the consequences of this, no? So this is the LM741 spin out. And you guys probably have seen itong dalawang input, no? So itong offset null is actually what you use to um, remove the offset voltage. Essentially, what you're gonna do is you put in a non-zero offset voltage into this pin of the package para ma-cancel out mo tong non-ideal offset voltage na to. That's your input offset voltage, right? Pin 8. NC. NC means not connected. So essentially, to NC. So nice, ang sabi niya. Essentially, kasi, um, you need to have an even number of pins, right? So either 6 pins or 8 pins. Kaso, ang TI, ang Texas Instruments, no, dinesign nila yung LM741 such that 7 yung nagamit nila. Sabi nila, oh no, 7 yung nagamit natin. So we're just not going to connect one of them. And that's what NC means. No? So if you see an NC in the pinouts, no, in the manual, ito, no? So that's what it means. Nakalagay no connect. And you can see right here, no? Nakalagay naman talaga dun sa offset null. This is your offset null pin used to eliminate the offset voltage and balance the input voltages, as we mentioned. Ganda ng picture nila dito. Ayan. So, yeah. So that's that's our first nonlinear non-ideality. It's your input offset voltage. Next nonlinear non-ideality is the input offset currents. So, I'm gonna draw the op-amp here, no? You may be able to imagine from the name kung ano ibig sabihin nitong input offset current na to. So, the input offset current is an imaginary current na na-experience ni op-amp from its inputs, no? And for no reason whatsoever, wink wink, we're gonna call that IB1 and IB2, no? So you guys can probably guess the reason for the existence of these input bias currents because IB yung okay baka dahil bias, no? But believe me, it's not. So essentially, we have these bias currents in the inputs of the op-amp, no? Of the order nanoamps, no? So you can find these guys in the range tens to hundreds of nanoamps, no? So that's your input bias and offset current, no? So input bias and offset current. Now you have two definitions, no? So the input bias current is the mean of these two currents, no? So the mean of these two currents and the offset current is the IOS daw ang pangalan niya is the difference between these two. Essentially yung offset current is the difference in currents of the two inputs and the offset voltage is the difference in voltage of the two inputs, right? So that kind of makes sense. Kaso yung general bias current natin is the average of the two currents, which also kind of makes sense, right? So we have two terms for this. It's the input bias current and the input offset current. Now, the input the input offset current is actually is going to is going to show kapag ganito yung ginawa. So, let's erase this sample values. So, let's say na wala tayong nilagay dun sa amplifier. So, in our usual times 2 amplifier configuration, no, or rather, inverting amplifier configuration, no? So, ito yung V-in mo. This is your R1, this is your R2, no? For an ideal op-amp, wala kang output dito, no? Wala siyang lalabas na output, wala siyang lalabas na output voltage. But, no? For an amplifier with an input bias and offset current, makikita nyo na mag-ground yun, di ba? So, actually, let me change the color of my let me just take refuge in another notebook. Yan. So, I have found the reason why, bakit siya nagsislow. Because I need to change to a new notebook kapag ganun. So, our analysis can go like this, no? So, ground yun. So then, kung ground yun, walang current yan, no? So, ito lang ang may current. Which means that V out over R2 is actually equal to IB1, no? Or, in other words, meron tayong ma-measure na V out, no? And you might say, okay, that's microvolts, no? Which is greater than noise, which is less than noise, no? So realistically, bakit? Kasi 'di ba 26 millivolts ang ating thermal noise or essentially yung thermal voltage ng isang electron, no? So, kung microvolts yung lalabas, then it's overridden by noise. But essentially, the input offset current still results in a non-zero bias in the output voltage, no? And the way that they tell us, no, to deal with this, at least that's what the slides say, no? So to be honest, I don't work with op amps that much. In Microlab we create op amps, but we don't. Okay, we use them, but I'm not analog. I'm digital, so not sure how much the experience the graduate assistants have or Ma'am Tess has with this. Probably has a lot. Anyway, we put in a third resistance R3 in order to offset this, no? So mangyayari kapag may R3 dito is ang totoong voltage na lalabas dito sa port na to, no? So let's call that Vx for now. Vx will then be equal to IB2 R3, no? Which makes it so that may current ka going here and here, no? So all you want to do is make this current as equal to IB1 as possible, no? Na baliktaran sila para mababa yung bias ng UV out. So, I hope that one makes sense. Ang tawag ulit dito, compensating input bias currents, no? So that's how we compensate for the input bias current. Right? I'm not gonna put specific numbers here. Actually, yung sinasabi ng slide is R3 is R1 parallel R2. But this doesn't actually completely remove the output bias, no? So, ang mangyayari dyan is ang current mo dito, no, if is going to be IB1 minus IB2, R3 over R1, no? And if R3 is R1 parallel R2, actually, let's see, no? Let's try to do, no, we're not going to do the math here because that would be, that would take us a little bit of time. So, exercise is left to the reader to show na magzi-zero ba to or not. So let's see, no? Anyway, the next, non-ideality, no, non-linear non-ideality is the slew rate. So the thing is, when you have an op-amp, tapos, okay, so meron kang op-amp, tapos raw siya, no? Hindi mo siya, um, so apparently, ganito yung configuration. Anyway, so yung input voltage mo, idea step siya, no? So at infinitesimal time, t equals 10 to the minus 29 or something like that, no? Yung difference ng dalawa, essentially it's just a very narrow step up, no? What do you think happens to the op-amp output? Sige, let's make it simpler. Let's make this ground and let's make the gain like 1. So, what do you think happens to the output of this op-amp kapag nag-step siya? 'Di ba, kung ideal siya, dapat kasabay niya, no? No matter how fast, kasabay niya dapat yung output. But in reality, everything has a transition time, no? And this is called your slew rate. So the maximum amount of the slope, no, versus time, no. So derivative versus time essentially is your slew rate. The derivative of the output versus time given an ideal input, no. And this one is interesting kasi what does it look like? It looks like the frequency response of the step response of an RC circuit. Uh, can anyone thumbs up if you guys know the step response of an RC circuit? Okay, so you've seen it before. And it kind of suspiciously looks like this. E di ba sabi natin kanina, the frequency response of the op-amp is kind of like this. You know what else is this? That's the step response of an RC circuit, no? Where the bandwidth frequency is 1 over RC, no? So essentially, the reason for the slew rate is because of the non-infinite bandwidth, no? So, that means that this non-linear non-ideality is actually related to a linear non-ideality, right? It's just called a non-linear non-ideality because it causes non-linear distortions in your output, no? As in, well, of course, no, this is exponential, it's not linear, right? So that's the slew rate, no? And those are your 3 non-idealities. So let me just copy this back into sige, let's write it all down. Um, so ano meron tayo? Real op-amps have, no, linear non-idealities. Of those, there are 4, no? Rn is not infinite. Rn is not infinite. Ang liit nito. Naka-strike through siya. R out is not 0. The gain, no, the open loop gain is not infinite. And also, the bandwidth is finite, no? So there is an end to the bandwidth, no? As in ito, no? That's this thing. For nonlinear non-idealities, we have ano ba? First off, no, input bias voltage, or rather input offset voltage. We have input offset current or bias, no, input offset slash bias current. Both of them are captured in the concept of the IB1 and IB2, no. Actually, let's write it down here, no. So offset is the difference, no. So OS is the difference between the IB1 and IB2, and the bias is the average of both. Lastly, no, we have slew rate limitations. All right, so these are your linear and nonlinear idealities. Nonlinear idealities, we only provide that for reference, no, so that you guys know that these things exist. Though it's up to Searchicho whether or not they'll appear on the problem, no. But for examples, let's focus on the linear non-idealities for now, no. So examples.
Because the reason why they're asking for it is to match the aesthetic if you get consistently. Check on it. If it looks nice, nothing feels off to you, then
Sir, ask ko lang, finally po ba ang bandwidth sa non-linear?
then ask for our
Yes. So both the linear, like for real op amps, both of these apply, no? So it's not like meron kang op amp na non-linear lang yung non-idealities or linear lang yung non-idealities. For real op amps, both of these apply. So probably short answer is kapag may nakita kang slew rate limitation, then that means your op amp also has a finite bandwidth. So it's implied by the existence of slew rate limitations. All right. So for finite gain, no? So let's say na meron tayong, again, no, gas-gas na yung circuit, but let's use it again. Meron tayong R1, meron tayong R2, no? Tapos meron tayong output voltage and then input voltage. This is your inverting input. All right. So for this circuit, let's make it smaller. And so for this circuit, no, actually that's way too small. And so for this circuit, alam natin, no, na the gain, no, not open loop gain, no, closed loop gain, or just the gain itself, right, is of an inverting amplifier na R2 over R1, no? So, yan, R2 over R1, right? And let's say, for example, na R2 equals 2K, R1 equals 1K, no? So, magiging negative 2 yung gain natin. Now, let's replace this op-amp with the model of a real op-amp with linear non-idealities, no? Or, never mind, sige. Let's first assume na, let's just apply one non-ideality. Now, open loop gain is not infinite. So, if the open loop gain is not infinite, may magbabago dun sa analysis natin, no? So, here, no? Let's also note, no, but R out is still 0, Rn is still infinite. Yan. So, anong mangyayari dito sa circuit natin? Well, what we would know is that V out would be the open loop gain times the inverting minus the non-inverting input. No? We know that this is 0, so that's negative AOL V minus. No? So that's one of our equations. Let's take a second equation by doing KCL, no, on this node. So you have V minus V in over R1 plus V minus V out over R2, no? That has to be equal to 0. Bakit? Kasi infinite pa rin si Rn, so there's no current passing through that. Right? So, math, let's just skip the algebra. But what you would get is V out over V in, no? Which is your actual gain, becomes scaled, no? So you have R2 over R1 up here, no? Your original gain times 1 over 1 plus R2 over R1 times the open loop gain, no? So ito siya. This is what you'll get from solving these systems of equations, no? So getting from here to here is once again left as an exercise to the reader. But, you know, that's just 2 equations to 1 node. Tapos linear naman lahat. So that should be doable. Right? So, there's also one other one other simplification that we can apply to this really is that we can name the ideal gain as the ideal gain in order to get this equation, no? So now, given a value of a non-infinite gain, we know how much the gain is affected, no? So, for example, no, dun sa slides, meron silang example na if negative 2 yung gain, no, as what we had, no? Ano yung AOL for gain, okay, for A to drop by 1%. So, in this problem, ang tinatanong nila is, you want the gain to drop by 1%. So, the new gain has to be 2 minus 0.01 times 2, no? Or plus, no? To drop by 1% versus the negative 2, no? So, this would be negative 1.98 yung totoong gain natin, no? And all you have to do is to equate this to the equation that we have, no? So if we equate this, we put negative 2 there and negative 2 there. We have one equation, one unknown, and we get that, ano yung nakuha nila? 297. And this is exact, no? I remember I did this, and exact yung answer, no? Wala siyang decimal points. All right? So an open loop gain of as low as, no, this is very far from infinity. This is just hundreds, no, but it gives just a 1% drop in the open loop gain of a feedback amplifier, no, which is quite something, no. So we don't actually need them to be all that ideal, mga op-amp. Right? Anyone have any questions about this? All right. So now let's do an analysis involving all of the different parameters of, again, yung inverting op-amp natin. Yung inverting amplifier configuration natin. Actually, Okay, let's take a small break, like 5 minutes, while I create the um attendance, no? So, sige, 5 minutes. Alright, sige. So, nasend ko na yung attendance, no? Both Discord and here. So, now let's deal with a real op-amp, no? A real, meaning I'm going to put in a 1 kilo ohm resistor here and a 3 kilo ohm resistor here. Tapos ito yung output voltage natin. Now, if this were, no, an ideal op-amp, right? If this were an ideal op-amp, your gain would be 3, right? Now, let's do it for a real op-amp with all of the nonlinear non-idealities, no? So, including nonlinear non-idealities, we have input resistance, no? We also have, sige. This is A open loop times, so this is Vx, no? So let's call that Vx. So we put Vx there, right? Because this is actually V minus, tapos V plus. Actually, no. Sige. Let's make that V minus para hindi confusing, no? Right. Hindi ko lang gustong isulat yung V minus kasi para siyang underscore. Tapos we have an R out, no? And let's make that 500 ohms. 200 ohms. Ayan. Alright? So, is everyone convinced na ito yung model ng op-amp natin? Tama naman, di ba? So, we just have an R in, we just have an R out, and an open loop gain. Di ba? So, if you want the slides version which shows the triangle, then here, look at this picture, no? So it's the same picture. And that's a meme, right? It's the same picture, sabi niya. So that's these are the same picture, you just put stuff inside the triangle, no? Okay, never mind. There's a load resistance. It's not exactly the same picture. So the load resistance, right? So the load resistance would be 1 kilo. And that gives us all of the circuit components needed, no? So the goal that we want is find the real gain, no? So how do we approach this? Well, by the powers of our circuit analysis skills. Bakit? Kasi we have resistors, we have dependent sources, no? So yun lang naman yung talaga yung kailangan natin gawin. All we need to do to find the real gain is to find the V out over V in of this circuit, no? So let's put this in our pocket. Yeah, let's put it in our pocket. Yeah. Yeah. So given that, so KCL number 1, we have that V minus times 1 over 1K plus 1 over 3K plus 1 over 500. Actually, sorry, hindi ko lalagyan ng numbers for now, no? Para alam nyo sa our to. So ilagay natin yan dyan. So 1 over Rn plus 1 over R1 plus 1 over Rin, 1 over R2 minus yung contributions, no, from V in and V out. That's 1 over R1 minus V out times 1 over R2 is equal to 0. Right? So does this KCL make sense? Pinactor ko na kagad siya, no? Kasi essentially by superposition, right? What you get is the voltages that the currents from V minus going against the currents that are due to V in and V out, no? That's KCL number 1. We have KCL number 2, which is at the node V out, no? So I think this is how Ma'am Tess does things. Yeah. So KCL at node. So let's sum up the contributions from V out. We have RL plus 1 over R2 plus the V R out, no? So 1 over R out, no? Tapos ang opposition niya has the V minus times 1 over R2 also minus the contribution of the open loop gain times V minus, no, which is your ED now, times 1 over R out
And he got the
equals 0. No? So this is your, and we can further simplify this one actually. 1 over RL plus, okay, we can further simplify this one. So copy paste that one. Minus V minus 1 over R2 times negative V minus, right? Kasi V minus is negative ED, no? So actually, baliktad yan, no? Kasi ito si ED, right? So, so 0 minus V minus, ang i-multiply mo sa AOL, no? So, ito yung, so negative actually yung voltage na lumalabas, right? So, V minus times R2 minus AOL 1 over R0 equals 0, right? So, that's your KCL and KVL equations, no? So, now, all you need to do here really is to isolate V minus dito sa taas. So, so if you isolate V minus, you'll get an equation that's like this. V in over R1, of course, plus V out. Antong nasa baba? Over R2. Over R2, all over. Ayan. Now, as early as now, no, we can actually perform some simplifications, no? That simplification is by saying that Rn is actually extremely huge. Rn is 500K compared to 1K and 3K, no? So actually, Rn, 1 over Rn rather, is much less than either of these, no? So we can actually do away with them. Kaso, I'm going to do the entire thing for now. And then, gawin lang natin yung simplifications later on. But I tell you, it would be much easier kapag na-eliminate mo na si Rn dito pala, no? Sige. So that's isolated B minus. And then if you do that, you'll get something like this. So, na-isolate na natin si B minus. So, i-insert natin siya dun sa KCL at V out natin dito. So, let's copy paste this.
Or open a support ticket for this. So we're going through this, but for
Right? So, copy paste lang din natin itong V minus dito sa part na to, no? Substitution. Right. And now we have an equation of V out versus V in. No? So now we have an equation of V out versus V in, from which we can isolate V out over V in, and that should turn out to be a very big equation. No? So it's going to be this one. 1 over R out times 1 over R1 over 1 over R2 plus 1 over RL plus 1 over R out. So you can see the individual terms. So ito napunta doon. So ito napunta din doon. Natupag na siya. A over R out times 1 over R2 dito sa labas, no? And, I did tell you, it's going to be ugly. It's hard to do this, algebraic manipulation. But this is the real answer, no? So if you substitute everything, you should get something like minus 2.988. 984. 2.984 dito sa problem na to, no? Na nandun sa slides. Now, the reason why I did all of this by hand, no, which I don't think it's supposed to be shown by hand, to be honest, kasi medyo mahaba siya. But the thing about this is this is a beautiful equation that you can do a lot of simplifications with. Like what? No? As I said earlier, itong 1 over Rn is actually much smaller than either of these two. No? Or rather, really, all you need to know is that it's smaller than R1 plus R2. The conductance of R1 and the conductance of R2. Kasi ito is 500K, ito is 1K, and ito is 3K. No? So as early as the middle steps, you could have removed that contribution. No? Likewise, dito sa part na to, R out is 200. As opposed to R2 and RL, which are thousands. No? So we can actually remove RL and R2 here. No? Tapos dito, we have a gain multiplied by the conductance of R out. So this one is actually really dominant. Kasi this is 1,000 times 1 over 200. No? Or actually this, that's 1,000 times 1 over 200 versus 1 over 3K. No? So this one is actually beaten out. Matatanggal si 1 over R2. And then, the same thing happens here, no? So those are both the same term. So magiging ganun lang yon. And the final equation that you're left with is actually R0, R out, R1 over 1 over R out times 1 over R1 plus 1 over R2 plus gain, open loop, no, AOL yan, times over R out, R2. which gives you, and I'll show you the calculator, no? Almost exactly the same, no? So 2.988 to, this is 2.984, no? So those types of simplifications are actually, they save you a lot of pen work and they actually do work, no? But then again, di po ba dapat negative yung numerator? You're right. Negative yung numerator. Yeah. So your real gain is like this. No. To be honest, the thing that's actually asked for in the example is the percentage error of A versus 3, no? But this is left as an exercise, no? So tingnan nyo kung paano nyo i-compute yung percentage error from here. The answer is shown in the slides naman. Right? So that's that example. All right? Shortcut solution. KCL, KVL. No? So there's actually no mababago ba natin yung circuit to remove this? G2. Sobrang haba. Yeah. So essentially, when you have problem sets concerning this, no, you'd probably find na ganito nga siya. But really, it's just algebraic manipulation. No? So I'm pretty sure you guys have seen kasi this is really what happens in the circuit analysis courses, right? You have two equations, two unknowns, actually this two equations, three unknowns, but you want to relate two of them, so you just want to eliminate one of them. And it's all just algebra until you isolate what you really need. No? The way that that we do things though, no, in 51, for example, 51 in 131, no, which is the same course, no, it's just an old name, is that we do these simplifications because some things are like some of these really are in different universes of largeness or smallness. So, but to be honest, I didn't really pick this up quickly either. Yung pampabilis, no? So really your bread and butter will really be algebraic manipulation. Though what you can do, no? Substitute terms, no? So this is let that be A, let this be B, let this be C, no? And let's see, no? Ano yung itsura nung final answer natin written in that, no? So, this is C over R1 over AB minus C over R2, no? So, that actually this is what I see most students doing. Na nagle-let sila ng variable and then the answer is in terms of those variables and then they just calculate and turns out the answer is correct. So that also simplifies your solution. Naka-direct message pala. So the question is, may shortcut solution po ba? The answer is no. Unless you have these assumptions. All right? So that's that one. Now for the final part, I'm going to go to Sir Chicho's slides. And then we're going to see kung ano yung examples niya ng op-amps. No? That's slew rate. This is the same this is picture from the same manual na pinakita ko kanina. So, okay, typical op-amps are implemented like this, no? So meron kang difference amplifier, voltage gain, and output stage, no? And essentially, what happens here is that the output stage, siya yung nagpapababa ng R out natin. Yung voltage gain stage is siya yung nagpapataas ng gain. And yung difference amplifier is siya lang yung dahilan kung bakit dalawa yung input natin. No? It's the reason kung bakit pwede tayo magkaroon ng feedback amplifier. No? So, ano ang itsura nitong mga to? No? They look like these. And you'll see every one of these stages Actually, no, maybe not the last one, no? But most of these stages, makikita mo, itong unang dalawa is, I'm 100% sure makikita nyo sa dito sa course na to. So this is a differential pair, no? And this is your common source amplifier with compensation. So compensation is, sige, let's copy paste this because, it's actually a cool thing to talk about. Yan. So, in reality, no, makikita natin sa course na to is paano to? This one, I'm not sure kung anong lesson to, but you call that a differential pair. But this one is a common source amplifier, which is actually the next lesson. This one is tapos this one, no, the capacitor, the reason why there's a capacitor there is called compensation, which is, ayan ko yung ulit, that's 3, 4, 5, 6, no? So, topic 6. All right. So, with that, that's what a typical op-amp looks like. And with that, ends our lecture for today, and I'll see you guys next week. Face-to-face tayo sa Wednesday. All right. So, thanks guys, and I'll see you guys next week.
Hello po, sir.
Yes?
Para po dun sa what's it called? Sa problem set po. Kailan po ang due date? Is it on 11 po ba or on 7?
Ang due date is kung ano yung nilagay ko dun sa submission bin, which is 11.
Okay, sige. Thank you po, sir.
Thank you po, sir.